Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the life of a single proton. Not just any proton, but one we will follow from the very first moments of the universe all the way to the end of time itself. We'll watch it drift through the birth and death of stars, pass silently through the long shadows of cosmic history, and perhaps even witness it become the very last piece of matter left in existence. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. We begin not in the middle of anything, but at the very beginning, or at least as close to the beginning as physics allows us to imagine. Picture a moment so small and so brief that even calling it a moment feels like an exaggeration. The entire universe, every star, every grain of sand, every thought you will ever have, is compressed into something smaller than a speck of dust. It's not even really there in a way you could point to. It's a state of everything at once where space, time, energy, and the seeds of all matter are folded tightly together. And then it changes. The change is not like a bang from a drum or the crack of a thunderclap. There is no sound. Sound needs air, and there is no air yet, no space for it to travel. Instead, it's more like the opening of a flower in a single impossible heartbeat. The universe expands, stretching itself in every direction at once, faster than anything can move, because in these first fractions of a second, the rules that will later limit speed have not yet been set in stone. This is the era of cosmic inflation, a growth so sudden and so smooth that the entire fabric of reality swells from subatomic to cosmic in less than the blink of an eye. In that rapid breath, the energy locked within the newborn cosmos begins to cool, and as it cools, it changes. The uniform smoothness trembles with quantum ripples, tiny differences in density that will, billions of years from now, shape where galaxies and stars will gather. But in this young and fiery world, those ripples are just whispers in a roaring sea. The particles we know today, the protons, neutrons, electrons, have not yet taken form. Instead, the universe is filled with a dense and glowing broth of quarks, the smallest known building blocks of matter, dancing with gluons, the carriers of the strong force that will eventually glue them together. There is light here too, in the form of photons, not the kind of light that can shine in a room, but light as pure energy, scattering endlessly from one particle to another in the thick, hot plasma. Our proton does not exist yet, but it is already written into the physics of this place. The strong force, one of the four fundamental forces that will govern all matter, is just beginning to pull quarks into combinations. This is no simple process. It's a chaotic marketplace where quarks and antiquarks appear and vanish, where gluons constantly exchange their hold, and where energy and matter are so interchangeable that a single collision can turn one into the other. A mere millionth of a second after the beginning, a span that feels infinitely small, yet holds the first crucial steps. Some of these quarks settle into stable trios, 2 up quarks and 1 down quark, held tightly together by the strong force, forming the very first protons. Others arrange themselves as neutrons. In a universe still unimaginably hot and dense, these are the first particles with the potential to last. Our proton is one of them, newborn, featureless, unthinking, yet destined for a life longer than any star. At first, it drifts through a sea of siblings, colliding, scattering, and occasionally fusing with a neutron to form the nucleus of a light element. The young cosmos is already a restless workshop, fusing protons and neutrons into hydrogen, helium, and a trace of lithium. These first elements are simple, but they are the foundation stones of all future complexity. Even now, our proton does not know where it will end up, though perhaps knowing is the wrong word for something without a mind. It simply exists, as it will for eons upon eons. Around it, the universe is still glowing like a furnace. Every point is so full of energy that no atoms can yet survive for long. Electrons, lighter and quicker than protons, rush past and are knocked away almost immediately by the constant blizzard of photons. This is the world our proton has been born into, a vast seething ocean of matter and light, expanding ever outward. It has no awareness of the cold and dark to come, of the stars that will one day call it into their hearts, of the unimaginable distances it will travel. For now it is just one of countless billions upon billions, each carried along by the tide of an infant universe, not yet a witness to time, but already part of it. Somewhere in this radiant chaos, the seeds of stillness have already been sown. Gravity is pulling matter ever so slightly toward matter, creating invisible threads across space. In the far future, these threads will weave the first constellations, the first galaxies, the first places where our proton will have a home. But for now, it drifts in the endless, beginning weightless, mindless, unhurried. Because in this era, everything is still so young that even forever hasn't started yet. The first few minutes of the universe are not loud. They are not even bright in any way that an eye could see. They are instead a deep and constant glow, a warm radiance filling every direction, not yet shaped into points or patterns. The expansion has slowed from its frantic inflation, but it is still rapid enough to carry everything farther apart with each passing moment. The heat is still intense, hotter than the heart of any star that will ever exist, but it is cooling, slowly, like water taken off a flame, and as it cools, the contents of this young cosmos begin to take on more familiar forms. Our proton, along with countless others, is no longer just a loose particle in a shapeless crowd. Some protons find themselves in the company of neutrons, held close by the strong nuclear force to form the very first atomic nuclei. This process, called nucleosynthesis, is happening everywhere at once. It is not a matter of choice or chance in any personal sense. It is the inevitable chemistry of a universe still soft enough to be shaped, but already ruled by laws as unbreakable as the bonds between its particles. Most of what forms in these first minutes is simple: hydrogen, with its single proton at the centre, and helium, with 2 protons and 2 neutrons bound together. There is a small sprinkling of lithium and beryllium, fragile in the harsh conditions, but even this small diversity marks a shift. The building blocks for everything that will come are already here, adrift in a vast and growing space that is still without structure. It is tempting to imagine our proton's world as empty and quiet, but at this stage it is anything but. The density is still immense, and particles are packed close enough that collisions happen in rapid succession, like dancers brushing past one another in a crowded hall. Photons, particles of light, are everywhere, streaming in all directions, bouncing from one charged particle to another in a constant exchange of energy. Electrons dart through the crowd, but they cannot yet settle into stable orbits around nuclei. Every time they come close, a passing photon knocks them away. Atoms, as we think of them, are still a long way off. This is a restless era, but it is also short. Within the first few minutes, the temperature has dropped enough that fusion slows, then stops. There is no longer the heat or pressure needed to push protons and neutrons together into new nuclei. The universe, in effect, has made what it can for now, and will spend the next hundreds of millions of years simply cooling, expanding, and waiting for gravity to take its slow, patient hold. Our proton is part of a hydrogen nucleus, just itself standing alone, drifting among the helium and lithium, all of them moving with the flow of expanding space. There is no up or down, no preferred direction. Movement is relative. What matters is that distances are growing, and with that growth comes a gradual thinning of everything. If it were possible to stand in this place, in which it isn't, you would see no edges, no centre, only a horizon that stretches and stretches as if it will never end. In these early days, matter and energy are still almost evenly mixed. Dark matter, the invisible cousin to the matter we know, is already here, shaping the gravitational landscape in ways that light cannot reveal. Where dark matter gathers in slightly denser knots, ordinary matter follows, falling into those unseen wells of gravity. This is the beginning of the great structures, the outlines of future galaxies, but they will remain invisible for a very long time, and so the proton drifts. Its life is not marked by events in the way ours is. It does not notice the passing of minutes or years. Time, to a particle like this, is only the changing of the space around it. It may travel immense distances, or it may remain close to the same companions for millions of years, but it has no awareness of the difference. It is simply carried forward by the expansion, like a leaf in a river that has only just begun to flow. The photons are its constant neighbours, moving far faster, passing by in endless streams. Every once in a while one collides with the proton, exchanging a fragment of energy, a nudge in direction, a reminder that nothing in this place is ever truly still. Yet even in this ceaseless motion, there is a kind of calm. The temperature falls degree by degree, the collisions grow less frequent. The universe, in its own way, is beginning to relax. Millions of years will pass before our proton experiences anything that could be called a change in environment. For now, the most important transformation is invisible, the slow fading of the background glow as light stretches into longer wavelengths with the expansion of space. The photons are becoming less energetic, less able to push electrons away from nuclei. A time is approaching, still hundreds of thousands of years ahead, when the electrons will finally settle down, forming stable atoms, and when that happens, the universe will shift again, in a way our proton could never anticipate. Until then, it remains a nucleus without a home, waiting for an electron to join it, floating through a vast and changing sea. The structures of galaxies, stars, and planets are only mathematical patterns at this stage, potential, not yet realized. The proton has no destination, yet it is already on a path that will take it through every chapter of cosmic history, even to the very last page. Somewhere ahead lies darkness deeper than this early night, and light brighter than anything that exists now. Our proton will be part of both, without question, because once it has formed, there is very little in the universe that can destroy it. The beginning of its story has been written in heat and expansion, in the quiet laws of physics, and in the slow drift of matter toward matter. The rest will unfold over billions of years, and all it must do is exist. There comes a moment when the collisions stop being constant, when the universe finally grows cool enough for the protons and electrons to form a lasting bond. It happens about 380,000 years after the beginning, a blink in the age of the cosmos, yet unimaginably long compared to the frantic rush of the first seconds. All across space, electrons spiral into place around hydrogen and helium nuclei, forming the first true atoms. The endless scattering of light finally ceases, and photons are free to travel in straight lines for the first time. It is a quiet revolution. There is no sound of celebration, only a change in the way the cosmos feels. Before, light could travel only the shortest of distances before being absorbed and re-emitted, bouncing endlessly like a traveller lost in a fog. Now, that fog has lifted. The light that escapes in this moment will keep travelling forever, stretching and softening with the expansion of space, until one day it will become the faint cosmic microwave background we detect today, the afterglow of the universe's childhood. Our proton is now part of a complete atom of hydrogen. An electron orbits at a respectful distance, held by the electromagnetic embrace of their opposite charges. Together they form something far more stable than either could be alone. Around them, billions upon billions of other atoms are doing the same, filling every cubic meter of space with the simplest possible building blocks. It is as if the universe has exhaled after a long and turbulent breath. But this new calm does not mean light will immediately return in all its brilliance. Quite the opposite. The birth of neutral atoms marks the start of an age that will be almost entirely dark. The stars have not yet formed. There are no galaxies, no glowing clouds, no beacons to light the way. The young universe drifts into a long night, a night that will last hundreds of millions of years. To our proton, the difference is subtle. Before, it was jostled constantly by the rush of photons. Now those photons mostly pass it by, unhindered. There is more space between encounters, more stillness. It is as though the crowded hall is emptied, leaving only a few figures moving quietly in the distance. The hydrogen atom it belongs to drifts through this darkness, following the invisible pull of gravity, gathering ever so slightly toward regions where matter is just a fraction denser than average. In this age, the architects of the future are unseen. Dark matter, invisible to light, yet heavy with mass, is quietly shaping the scaffolding of the cosmos. Its gravity pulls ordinary matter into vast loose clumps. These clumps will one day collapse into galaxies, but for now they are faint shadows, outlines drawn on a canvas too dark to read. The hydrogen atom containing our proton is caught in one of these slow gravitational currents. It does not fall quickly. Space is still, expanding, and that expansion works against the pull of gravity. It is a delicate balance, a contest that will play out for millions of years before anything dramatic happens. This is the quiet middle chapter between the heat of creation and the fire of the first stars. Nothing new is forged here. The hydrogen and helium formed in the first minutes will remain unchanged for now. Yet in this stillness, the conditions are aligning for the next transformation. Cold, diffuse gas will one day gather and tighten, and as it does, the pressure and temperature at its heart will rise again. But for now, there is only the slow drift. The darkness is not empty, far from it, but it is uniform. No single point stands out against another. Without light, there is no horizon, no way to tell how far one place is from the next. It is time without landmarks, without direction. For an atom, it is simply a matter of existing, carried along by the same currents as everything else. Our proton has no awareness of the scale of its journey. It cannot know that the forces moving it now will one day bring it to the centre of a newborn star, or that it will be part of cycles far longer than human imagination can comfortably hold. If it could notice anything, it might be the gentle tug of gravity, the faint shift in the background glow as photons stretch into longer, cooler wavelengths. Millions of years pass in this dark era. The dense knots of matter grow ever so slightly denser, while the empty regions grow emptier. The darkness deepens, and then, somewhere, a change begins. In the hearts of the largest clumps, hydrogen atoms start to gather in earnest, their numbers growing, their motions quickening under mutual gravity. The gas clouds grow warmer at their centres, and pressure builds. The moment is still far ahead for our proton. It has not yet reached the place where such a cloud is forming, but across the cosmos the first signs of light are stirring. The darkness will not last forever. The atoms are patient. The universe is patient. And so too is our proton, carried along in the silent tide, waiting for the night to break. This is how the great structures of the universe are born, not in sudden bursts, but in slow preparation, in ages where nothing seems to happen, yet everything is quietly arranging itself for the moment when change will be unstoppable. Our proton is part of that arrangement. its next chapter will not be gentle. It will be drawn into a place of crushing pressure and blistering heat, where the calm of these long ages will be replaced by the ceaseless fire of a star's heart. But for now, it floats in the last and longest night the universe will ever know, a night so vast that its ending will feel like the first sunrise. For hundreds of millions of years, the universe has been adrift in a vast and silent night. Hydrogen and helium, the simplest elements, have wandered through this darkness, gathering slowly into invisible shapes drawn by gravity's patient hand. Our proton has been one of them, carried along without urgency through currents that move so slowly they are almost impossible to notice, yet never stop. It is part of a small cloud, one of many, each drifting toward regions just a little denser than the empty space around them. The process is so gradual that, for most of its length, it feels as though nothing is happening at all. But over time measured in hundreds of millions of years, the balance begins to shift. The hydrogen cloud that our proton inhabits is no longer as diffuse as it once was. More atoms fall inward than drift away, and each one that joins adds its own pull. The centre grows denser. Gravity, which has been content to nudge and coax until now, begins to hold with a firmer grip. As the cloud contracts, the atoms are pressed closer together. Motion quickens. Collisions become more frequent. What was once a vast cold expanse now feels like a slow whirlpool, with everything spiralling toward the centre. The pressure builds silently, the way snow packs tighter under its own weight on a mountainside. And with the pressure comes heat, not from any flame, but from the simple fact that when matter falls inward, it gains speed, and that speed becomes warmth when the atoms meet. Our proton is drawn ever deeper toward the heart of this forming sphere. It meets others again and again, brushed by the soft electric pull of their electrons. But now the collisions are sharper, the energy higher. The temperature rises beyond anything that existed in the universe since the first few minutes after the Big Bang. At a certain point, the compression reaches a threshold. Deep in the core, where the pressure is greatest, protons are squeezed so close that their mutual repulsion, the electric force that normally keeps them apart, is overcome. The strong nuclear force, the most powerful bond in the known universe, takes over. Two protons meet not as passing strangers, but as partners in a fusion dance. One proton changes into a neutron, and together they become a nucleus of deuterium, heavy hydrogen. It is the first step in a chain of reactions that will turn hydrogen into helium, and in doing so, release immense amounts of energy. The ignition of nuclear fusion is not a sudden flash in a single instant. It is more like the slow spreading of warmth through frozen ground, the quiet tipping point when the balance changes and will never change back. From this moment on, the core will burn steadily, lightening each proton's load by turning part of its mass into energy that will push outward against gravity's endless pull. Our proton is part of this first generation of fire, not the small, long-lived stars of a later universe, but a giant among giants, what astronomers will one day call a population 3-star. These stars are massive, short-lived, and brilliant beyond anything our skies will ever hold today. They burn with the pure fuel of the early universe, with no heavy elements to dim or cool their light. And now that light comes at last. For the first time since the afterglow of the Big Bang, the universe is lit from within. Starlight streams out, crossing gulfs of space that have never seen illumination. It is not a single beacon, but the beginning of many scattered through the darkness, each one blazing into life in its own hidden cradle of gas and gravity. The long night begins to break. From the perspective of our proton, there is no ceremony. It has been swept into the core of a furnace, where it will spend millions of years pressed close to others, fusing, releasing its tiny portion of energy into the star's great radiance. Every collision it participates in Every reaction that changes its form is part of the star's heartbeat, a steady rhythm that will continue until the fuel is spent. Far away, in regions untouched by this dawn, the night still holds. But those regions will not remain untouched for long. The light from these first stars travels outward without resistance, carrying with it the power to strip electrons from atoms once again, rionizing the universe. Slowly, patch by patch, the darkness will be replaced with a dim cosmic haze until starlight becomes the rule rather than the exception. In the great story of matter, this is one of the turning points. The quiet atoms that formed in the universe's first 500,000 years are now entering their second act. Gravity has gathered them into structures, heat has lit them into stars, fusion has begun to make new elements that never existed before, and our proton, one among countless others, is in the centre of it all, no longer drifting in stillness, but bound in the heart of a blazing giant. It will not remain there forever. The life of a massive star is brief, a constant burning toward an inevitable end. But for now, the proton's surroundings are alive with energy. The space around it a constant blur of light-speed particles and dense plasma, the airless roar of fusion that can be heard in no human sense but is felt in every trembling atom. The long night is over, and the dawn, once it has begun, will never be forgotten. Inside the newborn giant, the environment is nothing like the silent drift of space that our proton once knew. Here, everything moves with purpose, driven by temperatures of millions of degrees and densities so high that the space between particles is measured in unimaginably small distances. Every atom is stripped bare, electrons wandering freely in a sea of charged particles, all bathed in the energy of relentless nuclear fusion. It is a place where matter is constantly changing form, where the boundaries between one state and another are blurred by heat and pressure, so extreme that the familiar rules of calm, solid matter no longer apply. Our proton's life here is one of constant encounters. It begins as part of a hydrogen nucleus, meeting others in fleeting but decisive collisions. When two protons come close enough, the strong nuclear force pulls them together in defiance of the repelling electric charge they both carry. In the process, one of them transforms into a neutron, releasing a positron and a neutrino, tiny messengers of the reaction, and binding itself with its partner to form deuterium, a heavier version of hydrogen. For our proton, this is the first transformation it has ever experienced. Yet it happens so naturally, so inevitably, that there is no pause before the next step. Soon, a third proton joins the pair, forming helium-3, and in the crowded furnace, helium-3 nuclei collide with one another to produce helium-4, the stable form we are most familiar with. Each step releases energy, not in an explosion but in a steady outpouring, a river of light and heat that streams outward to the surface of the star and beyond into the cold reaches of space. This process is more than just the making of helium. It is the first link in a long chain of alchemy that will eventually transform the universe. While most of the hydrogen here will end its life as helium, a fraction will go further. In the later stages of the star's life, helium itself will fuse into carbon, then oxygen, and eventually into elements like neon, magnesium, and silicon. The heaviest elements, such as iron, will not appear until the star's final moments, but the seeds of that future are already here in the star's core, where every reaction builds upon the one before it. For our proton, the journey is a series of roles in this vast nuclear theatre. For millions of years it may remain part of helium, cycling through reactions that swap partners and forms, its quarks rearranged but never destroyed. In some moments it will be bound tightly with neutrons, in others it will be set free again as a lone proton, only to be pulled back into another reaction almost immediately. In the crush of the stellar core there is no true stillness. Every particle is either moving, colliding, or preparing to. The energy released by these reactions does more than light the surrounding space. It holds the star together, creating an outward pressure that balances the weight of all the matter pressing inward. Without fusion, the star would collapse under its own gravity, growing hotter and denser until something catastrophic happened. But with fusion, there is equilibrium. The star breathes in its own way, a steady, measured rhythm of burning and shining. Outside the star, the universe is changing too. The first generation of massive stars is lighting up the cosmos, ending the dark ages. Their light travels vast distances, breaking apart hydrogen atoms in interstellar space and allowing the first galaxies to take shape with clarity. The once empty darkness now has points of reference, brilliant short-lived beacons marking the places where matter has come together most fully, inside. Our proton continues its part in the cycle. It may spend millions of years locked into helium, or it may find itself joining reactions that create carbon. These heavier elements are rare here, in this first star, but their presence is a promise of what will come in later generations. Stars will eventually be born already rich with these elements, making planets, oceans, and life possible. But for now, the star is young, and its work is just beginning. The heat and light we see from such a star is ancient by the time it reaches our eyes, but in the moment of its creation, it is a constant, steady gift. Every reaction in the core sends out a photon, which may spend thousands of years bouncing from particle to particle inside the star before finally escaping into open space. Some of these photons will cross billions of light years before meeting an observer. Others will be absorbed by nearby clouds of gas, sparking new rounds of star formation. All of them are part of the legacy of fusion, the spreading of energy outward from a single heart of burning hydrogen. Our proton does not know that it is part of something vast and beautiful. It cannot know that the light it helps produce will one day shine on planets, or that the elements formed here will seed worlds it will never see. It simply follows the laws of physics, as it always has, moving through the steps laid out by the conditions around it. Yet in doing so, it becomes part of a transformation that will shape the entire future of the universe. The alchemy of fire is not a single moment. It is an ongoing act, repeated countless times every second in every star that has ever lived. And here, in this first generation, it is new, not because the laws are different, but because the universe has only just learned to make light from matter. Our proton is among the first to take part in that lesson, and in time it will carry the memory of this heat and light into the next chapter of its impossibly long life. Massive stars do not grow old quietly. They live with a kind of urgency, burning through their fuel far more quickly than smaller, gentler suns. While a star like our Sun may last for 10 billion years, the giant that holds our proton will live only a few million. Its size is both its strength and its undoing. The greater the mass, the stronger the pull of gravity, and the greater the need for fusion to push back against that inward collapse. The result is a furious pace of burning, a constant cycle of fusion that leaves no room for idleness. Our proton has been through many transformations during this time. It began as hydrogen, then became part of helium, and perhaps later part of carbon or oxygen. In each form it has been bound tightly with other nucleons, sharing in the energy released with every step of the chain. For millions of years, it has known nothing but the heat and pressure of the stellar core, a place where distances are short, temperatures are high, and every atom is stripped to its bare nucleus. But eventually the balance begins to tip. The hydrogen in the core has long since been fused into helium. The helium has in turn been burned into heavier elements, each stage occurring faster than the one before. Carbon into oxygen, oxygen into silicon, silicon into iron. A sequence that feels inevitable once it begins. Each new fuel lasts for a shorter span, until at last the core is filled with iron, an element that cannot yield energy through fusion. Iron is, for a star, the final barrier. It cannot be burned to keep the star alive. Instead, it sits heavy in the centre, a sign that the end is near. For our proton, this moment is a turning point. It is part of an atomic nucleus somewhere in the outer layers of the core, still fused into matter that can release energy, but it is no longer far from the final, unburnable heart. The outward pressure from fusion begins to falter, and gravity, which has been held at bay for millions of years, reasserts itself with overwhelming force. The star begins to collapse inward. The collapse happens with terrifying speed, though even here, in this telling, it is not a violent sound but a silent inevitability. The core contracts, temperatures climb to billions of degrees, and the density becomes so extreme that electrons are forced into protons, creating neutrons and releasing neutrinos in vast numbers. In an instant, the core becomes a ball of neutrons, incompressible and unimaginably dense. Then, just as suddenly, the collapse stops. The outer layers, which have been falling inward, crash against the solid neutron core and rebound. This rebound sends a shockwave rippling outward, tearing through the star's layers. Neutrinos flood out, carrying away energy, and the entire star is ripped apart in a single blinding event. This is a supernova, the death cry of a giant, the most powerful explosion the universe can produce short of the Big Bang itself. Our proton is caught in this storm. It may be part of a heavier element by now, perhaps locked inside the lattice of an iron nucleus, perhaps bound into oxygen, but the explosion unravels all bonds. Nuclei are smashed apart and reassembled in the brief chaos of the blast, creating some of the universe's rarest elements in fractions of a second. The intense heat and pressure forge gold, uranium, and other heavy atoms, scattering them into space along with everything else the star once held. For the proton, this is liberation. It is flung outward on a wave of stardust and light, travelling at immense speeds into the widening debris cloud. Around it, fragments of the star spread in all directions, cooling as they go, leaving behind only the collapsed core, now a neutron star perhaps, or a black hole, as the last remnant of the giant's once glorious life. The light of this supernova will travel across the cosmos, visible to distant galaxies, bright enough to outshine entire galaxies, for weeks or months. Its energy will seed nearby regions of space with the heavy elements necessary for planets, oceans, and life. And our proton, now once again free, becomes part of that scattering, a tiny traveller carrying the memory of the star's heat and the violence of its end. In the cooling debris, the proton drifts. For a time, it may remain part of a small clump of atoms, moving through the interstellar medium, a thin, quiet space between stars. It is no longer confined to the crushing depths of a stellar core, but it is also far from any place of warmth. The journey ahead will be slow. It may take tens of millions of years before gravity gathers it again into some new structure, perhaps another star, perhaps a planet. The universe moves at its own pace, and the space between events can be vast. But this is the nature of matter's story. It is not the rush of one lifetime, but the patient unfolding of many. A single proton may see the birth and death of stars, the rise and fall of galaxies, the slow drift of space into deeper silence. It may be bound into living creatures for a fleeting moment, or spend billions of years locked in the frozen rock of a dead world. It can be part of everything, and it can wait for anything. For now, our proton is simply a drift in the echo of a giant's last breath, a survivor of fire and collapse, carrying on through the next long chapter of the universe's history. After the brightness and fury of the supernova, the universe feels quiet again. The shockwave has long since passed, leaving behind a slowly expanding shell of dust and gas. Among that drifting debris is our proton, once hurled outward at tremendous speed, now slowed by the resistance of the thin interstellar medium. It moves without urgency, carried along in a great invisible tide of matter that will wander for millions of years before settling anywhere. The space between stars is not truly empty. It is filled with atoms and molecules, traces of gas left from earlier generations of stars, and fragments of heavier elements created in their deaths. Here, hydrogen, including our proton, mingles with oxygen, carbon, and other products of cosmic alchemy. Over time, gravity begins its quiet work again. This region is not dense enough yet for anything dramatic, but subtle motions are always underway. Clumps of matter form, drawing in more mass from their surroundings. Our proton finds itself caught in one of these clumps. The gathering is slow, almost imperceptible, but it builds momentum over millions of years. Gas clouds merge, dust grains collide and stick together. In the centre of the growing mass, pressure and heat rise, though not to the extremes of the giant star it once knew. Instead, the process will give rise to something smaller, steadier, and far longer lived. A star like our Sun. By the time this new star begins to shine, our proton has already travelled far from where it was born. It is part of a mixture of gas and dust orbiting the star in a wide flat disk. Within this disk, material clumps into larger and larger bodies, planetesimals, then protoplanets, each sweeping up more of the surrounding matter. In this way, the hydrogen that once drifted alone in the cold darkness finds itself woven into the fabric of a new world. In time, our proton becomes part of a water molecule, one of two hydrogens bound to oxygen. The journey from stellar core to planetary ocean has taken billions of years, yet for the proton, it is simply another chapter. Water is abundant on this young planet, filling seas and rivers, pooling in the shadows of craters, falling as rain. The world spins beneath a warm, steady sun, and in this warmth, chemistry takes on new forms. For the first time, our proton is part of something alive. It becomes incorporated into a green leaf, drawn up from the soil as water and lifted into the light. Inside the leaf, sunlight drives photosynthesis, splitting the water apart so its hydrogen can help make sugars, the energy source for the plant's growth. For a brief moment, brief only on the scale of a proton's life, it is part of a living cell, surrounded by the quiet hum of biological processes. It may pass from one form of life to another, from plant to animal, from animal back to soil, always part of the endless recycling that life depends on. The bonds it forms and breaks here are not as permanent as those in a star's core, but they are no less intricate. Each connection is part of a delicate web, a reminder that even the smallest particle can take part in something vast and complex. Eventually it returns to the ocean, perhaps carried in a raindrop or a river current, drifting with the tides under the pull of the moon. There it might remain for centuries, or it might evaporate again, rise into the sky, and fall back in a storm. Life on this planet is dynamic and restless, but for a proton, it is all a passing season, a momentary warmth in a life that will outlast the planet itself. The sun will shine for billions more years, but even it is not eternal. Over time, the balance of hydrogen and helium in its core will shift, and it will swell into a red giant. The inner planets may be swallowed, the outer worlds will be transformed. Long before that, however, our proton's place will change again. A collision between asteroids may scatter it into space. A comet might carry it to the outer edges of the solar system, where sunlight is pale and the cold is deep. Or it may remain locked in rock and soil until the slow erosion of time releases it. Whatever path it takes, the end of this chapter will be quiet, as the title suggests. The violent birth of the first star, the cataclysm of the supernova, those are far behind. Now the pace is slower, the surroundings gentler, the proton's role woven into smaller cycles. It has been part of the birth of light, the forging of elements, and now it has been part of the intricate dance of life. And as always, it continues onward, ready for whatever form the universe offers next. In the distance, other stars are forming, others are dying, and the great structures of galaxies are shifting slowly under the pull of gravity. For our proton, these are only the changing landscapes through which it moves. Whether in the heart of a star or the drop of a leaf, it remains the same, a tiny, enduring piece of the universe's long story. For billions of years, the star that has been our proton's home has burned with steady light. Its warmth has nurtured planets in close orbits, stirred winds and tides, and set the rhythms of life on at least one of those worlds. For most of its life, the star has changed so slowly that no observer on any planet could notice the difference. The fusion of hydrogen into helium in its core has been steady, balanced perfectly against gravity's pull. Seasons have come and gone, continents have shifted, and even whole civilizations might have risen and fallen under its light. Yet the star itself has remained constant. But nothing in the universe, not even a seemingly eternal star, can hold its form forever. Slowly, almost imperceptibly, the balance begins to shift. Hydrogen in the core becomes scarce, replaced by helium that cannot yet fuse in the star's current conditions. With less fuel for fusion, the outward pressure that once held gravity in check begins to weaken. Gravity responds, compressing the core, and in doing so, heating it to new extremes. This new heat ignites fusion in the layers around the core, and the star responds in a way that must seem impossible to any living world still orbiting it. It swells. The change is gradual on a human scale, but swift in the language of stars. The star's outer layers expand outward, its surface cooling so that it glows a deep orange red. It becomes a red giant, larger than it has ever been. Worlds that once orbited safely may now find themselves deep within its extended atmosphere, engulfed by heat and light. The quiet landscapes they once held, oceans, mountains, plains, are burned away, their rocks vaporized, their atmospheres lost to space. Our proton, perhaps still part of a molecule of water or locked in a grain of rock, is caught in this transformation. The rising heat strips apart molecules, freeing atoms to drift as gas in the swelling atmosphere. The gentle bonds that held matter in place for billions of years are broken in an instant. As the red giant grows, currents of hot plasma carry our proton outward, away from the core, away from the surface, and finally into space. It is no longer bound to a planet or a star. It is a traveller again. The red giant stage is brief compared to the star's long main life, lasting only a few million years. In that time, the star's outer layers grow unstable, and great clouds of gas are cast off into space. These clouds form a glowing shell, a planetary nebula, lit from within by the star's exposed hot core. The sight is beautiful, though it will not last long. The gas will disperse into the surrounding space, fading back into invisibility. At the centre of this display remains the core, now too small to be called a star in the way it once was, yet still incredibly hot and dense. This is a white dwarf, the remnant heart of the star, glowing with the heat of what was once a living sun. No fusion burns here. The light it emits is the fading memory of 1 billion years of fire. Over time, even this light will diminish. The white dwarf will cool, growing dimmer and dimmer until it is only a cold cinder drifting through the dark. Our proton does not linger to watch this slow fade. It has been carried far into interstellar space, moving outward with the expanding nebula. Around it are countless other particles, hydrogen from the star's outer layers, traces of heavier elements forged in earlier generations of stars. All of it is dispersing, thinning into the vast gulf between suns. Gravity will eventually gather some of it again, but that will take millions or even billions of years. The space it enters now is quieter than it once was. Billions of years have passed since the first stars lit the universe, and while galaxies still spin and new stars still form, the pace is slower. Gas is scarcer, much of it locked away in long-lived stars that will not end for trillions of years. The great age of stellar creation has passed its peak, and the era ahead will be one of gradual fading. Still, there is no sense of finality here, only transition. The death of a sun-like star is not an end, but a scattering, a returning of matter to the wider universe, ready for its next form. Our proton, freed again, drifts in the quiet light of distant suns, carried forward by the same expansion that began in the first moments of the universe. It has been part of a living world and part of a star's fire, and now it returns to the open sea of space waiting for the next chapter. Far behind it, the white dwarf glows faintly, a small and steady ember that will shine for billions of years more before going dark. Around it, the Planetary Nebula continues to expand, becoming more transparent with each passing millennium until it vanishes entirely. What remains is the silence of deep time, the slow turning of the cosmic wheel, carrying everything forward at a pace no eye could see, yet no force could stop. The death of a single star is a small event when seen against the whole sky. In any one galaxy, millions of other stars continue to burn, each with its own system of planets, moons, and dust clouds. Yet over time, even the vast canvas of the cosmos begins to change. From our proton's perspective, drifting freely now between the stars, the universe still seems full of light, but that light is not as abundant as it once was. Billions of years pass and the change is gradual, almost unnoticeable at first. It is not the sudden darkness of a lamp switched off, but the slow dimming of an evening sky after sunset. Starbirth still happens, but at a pace far slower than before. The raw material for new stars, the great clouds of hydrogen gas, has been depleted. Much of it is locked away in existing stars, and every new generation of stars leaves a little less for the next. In this era, the largest, brightest stars have already burned out. What remain are smaller, steadier suns, red dwarfs, stars so cool and efficient that they can burn for trillions of years. Their light is not bright white, but a deep, ruddy glow, faint compared to the hot, blue-white giants of the early universe. Yet these red dwarfs are patient. They sip their fuel instead of devouring it, stretching their lives across spans of time longer than all of cosmic history so far. For our proton, the journey takes it past these slow-burning embers. Sometimes it drifts close enough to feel the warmth of a red dwarf's light, but never so close as to be captured. More often, it passes through vast stretches of space, where the only illumination comes from distant galaxies. Even those galaxies are changing. Dark energy, the mysterious force driving the expansion of the universe, continues its quiet work. Space itself grows faster in its stretching, pushing galaxies farther and farther apart. Those that are far enough from our own galaxy recede so quickly that their light takes longer and longer to reach us. Eventually they cross a kind of invisible horizon. Beyond that horizon, their light will never arrive, no matter how long we wait. The night sky loses these galaxies one by one, like ships sailing over the edge of the world, their lanterns disappearing into the dark. The universe feels larger now, but also emptier. The great clusters of galaxies remain bound together by gravity, but between them the voids widen. Light from distant places is rarer, fainter and redder, stretched into longer wavelengths by the relentless expansion. The background glow from the universe's early days, once a warm bath of radiation, has cooled into near absolute darkness, its photons stretched into whispers far below what human eyes could ever detect. Our proton is unaware of the scale of this change, but it moves within it. The starlight it once knew as a constant background has grown thin. Regions of space that once held a steady sparkle now seem sparse. The great arcs of spiral galaxies still exist, but they are fewer in view, and those that remain are drifting farther apart. Yet this is not a time of absolute stillness. The red dwarfs that dominate the era are stubborn flames, and some still form new planets. For trillions of years, these small suns will be the only significant sources of light in the universe. Around them, faint warmth will persist even as the rest of the cosmos cools toward infinity. But red dwarfs are not eternal. Even they will one day exhaust their hydrogen, swelling briefly into brighter stars before fading away. When that happens, the balance of the cosmos will tip further toward darkness. The great chain of stellar birth and death will slow almost to a halt. As ages pass, our proton continues its slow drift. It may pass through the outskirts of a galaxy, skimming the edges of a star system before being carried onward by chance encounters. It may find itself caught in the pull of a dying star's gravity, only to be released again when that star sheds its outer layers. These encounters are rare now. The space between such events is vast, and the proton's path is guided more by the slow tides of cosmic expansion than by any single nearby object. The universe has entered a quieter age, but it is not yet silent. There are still stars to be born, still orbits to form, still bursts of light from the occasional supernova in some distant corner. But the overall rhythm has changed. The golden age of brilliant, short-lived stars has ended. The cosmos is settling into a slower, dimmer heartbeat. From the moment of the Big Bang until now, the universe has been defined by change, a constant unfolding of structure, light, and energy. But in the age of fading light, change begins to mean something different. It is no longer the rush of creation, but the steady retreat towards stillness as the bright chapters close one by one. Our proton remains, as it always has, simply moving through whatever the universe offers. It has been part of blinding fire and gentle oceans, of the brief spark of life and the long drift of darkness. Now it enters a chapter where light itself is rare, and where the distances between bright places grow beyond imagining. The night is coming, not as a sudden fall of shadow, but as a patient, inevitable dusk. Time has stretched far beyond anything the early universe could have imagined. Trillions upon trillions of years have passed since the first starlight broke the dark. Galaxies have thinned into loose gatherings of ancient stars and stellar remnants, all bound together in clusters that drift slowly through an ever-expanding void. The fast-burning giants have been gone for ages. Even the modest yellow stars like the Sun are long since faded. What remain now are the red dwarfs, the slowest burning, most patient stars ever to exist, and even they are nearing the end of their lives. For much of cosmic history, red dwarfs were the quiet keepers of light. They consumed their hydrogen with remarkable thrift, ensuring lifespans measured not in billions, but in trillions of years. Around them, planets could bask in steady warmth, for longer than the age of the universe as we know it today. But the fuel that lasts longest still runs out eventually. The final red dwarfs are now approaching that limit. They're cooler and dimmer than ever before, their glow a faint ember compared to the rich orange they once showed. In their cores, the last hydrogen atoms fuse into helium at an almost reluctant pace. The outer layers, once turbulent with convection currents, grow still. Energy seeps away into the coldness of space, and the balance between pressure and gravity begins to fail. When that balance tips, even a small star cannot resist change. The last stages of fusion turn helium into heavier elements, but these reactions are brief and incomplete. There is not enough mass for these dwarfs to collapse into neutron stars or explode in supernova. Instead, they shed their outer layers gently, if anything in this age could be called gentle, and leave behind a small, dense core. This is a white dwarf, much like the remnant of a sun-like star, but smaller, cooler, and born into a universe that has far less light to offer. Our proton by now may have spent countless ages inside the core of one of these fading red dwarfs. It could have been part of hydrogen for trillions of years, part of helium for more trillions after that, never once leaving the star's shelter. But when the end comes, it is released again, The expanding layers of gas carry it outward, scattering it into space. For the first time in trillions of years, it is free. The white dwarfs left behind are dim. Their light, weak to begin with, fades steadily as they cool. Eventually they will become black dwarfs, cold, solid masses of carbon and oxygen that no longer radiate heat or light. These objects will be almost invisible, detectable only by the faint gravity they exert on anything that passes nearby. They will not form new stars or planets. They will simply persist, waiting in the dark. The universe at this point is not entirely without light, but the sources are few. Occasional collisions between stellar remnants may flare briefly, releasing bursts of radiation, but such events are rare. Black holes still exist, slowly evaporating through Hawking radiation, but their energy output is tiny compared to the light of living stars. The background of the cosmos is colder than ever, its temperature approaching absolute zero. For our proton, the distances between encounters are vast. It drifts through interstellar, now almost intergalactic, space, passing black dwarfs, neutron stars and black holes. The once bright spiral arms of galaxies are gone, replaced by sparse constellations of remnants. The great cycles of birth and death that once defined the universe's history have slowed almost to a stop. Matter is no longer being reshaped into new forms at the pace it once was. Instead, it is locked into the quiet persistence of leftovers. If we could look back from this era to the time of galaxies teeming with stars, the change would seem almost unrecognizable. Where there was once a sea of light, there is now an ocean of shadow, punctuated by rare, faint glimmers. Time passes without seasons, without the rise and fall of stellar generations. The cosmos has grown old, and yet even here, the journey is not over. The proton remains what it has always been, a fragment of matter capable of enduring conditions no living thing could survive. It has weathered the collapse of giants, the freezing darkness of interstellar space, the long shelter of smaller suns, and now the stillness of a universe with no new stars to offer. In its quiet persistence, it is a witness to everything the cosmos has been, from the first fraction of a second after the Big Bang to this far distant age, when light itself is a rare event. Some of the black dwarfs will remain for unimaginable lengths of time before they decay. Some will persist until the last moments before matter itself begins to break apart. But for now, they are simply cold stones adrift in a boundless night, each holding the memory of a star's warmth deep in its frozen heart. Our proton drifts on, not seeking and not avoiding, simply existing in the space between all that remains. The silence around it is complete, but silence has been its companion before. What has changed is the scale. The absence of light is now not a pause between events, but the defining condition of the cosmos itself. The long-burning stars have gone out. The age of starlight is over. The universe, once a place of constant creation, has settled into its longest chapter yet, a chapter where time stretches forward without the punctuation of new beginnings, and where the few remaining witnesses, like our proton, carry the memory of everything that has passed. The universe has entered an age where change is no longer measured in the bright rise and fall of stars, but in the slow rearrangement of what they have left behind. The great furnaces that once lit the cosmos are cold. The clouds of gas that once swirled into new suns have been spent, scattered, or locked into dead masses of matter that will never shine again. What remains are remnants, the long-lived cores of extinct stars, neutron stars, and black holes, drifting through a darkness so complete that light is a rare and fleeting thing. Black dwarfs dominate this landscape, each one the quiet tomb of a star that once warmed planets and lit the night skies of distant worlds. They are the cooled remnants of white dwarfs, so cold now that they blend almost seamlessly into the blackness around them. They do not glow, they do not warm anything. The only hint of their existence is the way their gravity tugs on passing matter, bending the paths of objects that come too close. Then there are the neutron stars, dense, city-sized spheres of matter left behind by supernovae long past. Their magnetic fields are immense, their surfaces hard and unyielding, but without a supply of fresh energy, they too grow cold over unimaginable spans of time. They remain as silent beacons, not broadcasting light, but existing simply because nothing in the universe yet has the means to erase them. And still deeper in the shadows are the black holes, the most enduring of all stellar remnants. Their gravity is so absolute that not even light can escape, and so they sit as dark wells in the fabric of space, invisible except for the rare occasions when a passing fragment of matter falls in, releasing a final flicker of the energy before vanishing forever. Some of these black holes are the remnants of massive stars, others are the supermassive ones at the centres of ancient galaxies, now left to preside over starless domains. Our proton moves among these remnants. It is not bound to any one of them for long, though over the course of eons it may fall into orbit around a black dwarf or pass close to a neutron star. The gravitational pulls are subtle but constant, shaping its path like slow-moving currents in an ocean. Between these encounters are stretches of pure emptiness, regions of space so vast and so uniform that nothing breaks the monotony for millions of light years. The absence of light changes the nature of time here. In earlier ages, events could be marked by the life cycles of stars, the flare of a nova, the expansion of a red giant, the sudden brilliance of a supernova. Now there are no such signposts. The passage of 1 trillion years feels no different from the passage of 10 trillion. The universe moves forward, but without the markers that once made its story vivid to the human imagination. And yet, even in this stillness, there is motion. Black holes slowly lose mass through Hawking radiation, evaporating over inconceivably long time scales. A neutron star may eventually collide with another, sending out one last ripple of gravitational waves before merging into a larger remnant or collapsing into a black hole. Occasionally, the chance meeting of two black dwarfs might ignite a brief flash, a tiny echo of the supernovae that once shaped galaxies. But these events are so rare that entire cosmic epochs can pass between them. For our proton, these are the rare moments of interest in an otherwise quiet journey. It might be swept into the outer edge of a black hole's accretion disk, joining a final cascade of matter spiraling inward before being torn apart and reduced to pure energy. Or it might avoid such fates entirely, drifting freely until the very fabric of matter itself begins to break down. Whether it participates in these rare events or not, it remains a witness to them simply by existing in this time. The great structures of the universe are also changing in subtle ways. Galaxy clusters that once held thousands of stars are now little more than scattered collections of remnants bound together loosely by gravity. The empty spaces between them have grown so wide that travel from one cluster to another is effectively impossible. The expansion of the universe continues without pause, stretching space itself so that even these remnants grow farther and farther apart. If there were an observer in this era, someone capable of perceiving the vast scales and slow movements, they would see a universe in its quietest form. No longer a place of constant creation, it has become a place of endurance, where the objects that remain are those most resistant to change. The beauty here is not in brightness or activity, but in persistence, in the way matter holds its form even when there is no longer any reason for it to do so. Our proton continues its long drift, unhurried, unchanged. It has been part of fire and water, rock and air, life and death, and now it is simply part of the dark. The journey is not over, but it has entered a chapter in which waiting is the only constant. The universe is still here, still vast, still moving toward whatever comes next, and the proton, as always, will be there to see it. Through every chapter of cosmic history so far, our proton has endured, It was there when the first stars ignited, when galaxies began to spin, when planets formed from dust, and when all of that crumbled into silence. It has been part of fire and part of ice, part of light and part of shadow. In the vast ledger of the universe's transformations, the proton's entry has remained unchanged. That endurance is not an illusion. The proton is, as far as we can tell, one of the most stable things in existence. Experiments on Earth, far removed in scale from the lifetimes we're speaking of here, have searched for any hint that protons decay. None have been found. From this, physicists have placed a lower bound on its lifespan, at least 10 to the power of 34 years. That is a number so large that even the entire history of the universe so far, around 13.8 billion years, feels small against it. If the universe's current age were a single day, the proton's minimum lifetime would be longer than all the days in all the years that any star will ever see. And yet, some theories suggest that even this is not the whole story. The proton may not be truly eternal. It might be that, given enough time, it will eventually fall apart, not violently, but quietly, releasing its energy in a faint whisper of lighter particles. In that moment, the proton as we know it would cease to exist. What remains would be photons, neutrinos, and other ephemeral bits of the quantum world, destined to spread endlessly into the dark. For now, these ideas are only that. Ideas. We have never seen a proton decay, nor can we easily imagine witnessing one when the waiting time is longer than any human history could contain. But physics, as it has often done, asks us to consider scales that strain the limits of our intuition. Just as stars once thought immortal eventually grew old, so might the proton's apparent permanence one day prove to have an end date. If this is true, then forever, in the language of matter, is simply a longer chapter, not an infinite one. Even something as enduring as our proton is not immune to the slow, patient unraveling that time demands of everything. Perhaps the decay of a proton would not feel like an event at all, no more dramatic than a single snowflake melting in the spring sun. But if it happens, it will be the moment when the last tangible piece of the familiar universe lets go of its form. In the vast stretches of time between now and that possible moment, the proton continues its journey through the dark. Stars have long since gone. The black holes still remain for a while, pulling in stray matter, but they too are fading. The universe is colder than it has ever been, quieter than any human mind can imagine. The distances between particles are enormous, and yet the proton persists, a lone traveller in a space where almost nothing else remains. It has survived collisions at nearly the speed of light, the crushing gravity of stellar cores, the searing heat of supernovae, and the slow, drifting stillness of interstellar space. If anything can endure until the universe itself changes its nature, it would seem to be this, a particle so small and so steadfast that it can carry the memory of everything. But the thought of decay lingers, not as a threat, but as a reminder. If protons do eventually break down, then all the structures of matter, the atoms, the molecules, the worlds, the remnants of stars, will dissolve into light and subatomic fragments. There will be nothing left that could hold together in the ways we now recognize. The universe would enter a chapter not just without stars or galaxies, but without solid matter of any kind. The idea is hard to picture. Matter is the texture of the universe as we experience it. The stones, the oceans, the air, the bodies we inhabit. Remove it, and all that remains is a web of energy and space without landmarks, without shape. And yet, for all its strangeness, it would still be a continuation of the same story our proton has been living since the first second after the Big Bang. The transformation would be one more in a chain of changes that began before there were stars, before there was light. If our proton could think, perhaps it would not worry about this possible end. For something that has lasted through so much, the idea of ceasing after 10 to the power of 34 years might not feel like an ending so much as the closing of a book, already too vast to read in one lifetime. In the language of the cosmos, even decay is just a different kind of persistence. The energy it releases would continue its journey, just in another form. And so the proton drifts on, unaware of how long it has left, if indeed there is a limit at all. Around it the universe grows older. The remnants of black dwarfs and neutron stars are cold and dark. Black holes still lurk, but their shadows are fainter, their lifespans ticking down slowly in a process too gradual to notice. Beyond them, the distances stretch endlessly, the expansion of space carrying everything farther from everything else. It is a long wait, but waiting is what the proton does best. Whether it stands for eternity or only until some unimaginable clock runs out, it remains for now as it has always been, a single, steadfast piece of the universe's oldest story. For so long, black holes have been the final word in endings. They are the places where matter vanishes, where the gravity is so intense that even light cannot escape. Across cosmic history, they have consumed stars, gas clouds, planets, and anything else that wandered too close. For trillions upon trillions of years, they have been the silent anchors of galaxies, even when those galaxies have grown cold and empty. In the age of remnants, they seem like they would last forever. But forever, in physics, is a flexible word. Black holes, it turns out, may have a kind of leak. Not a leak in the way a cracked container loses water, but a subtle, quantum-scale process that slowly bleeds them of energy. Stephen Hawking first described it, a faint glow now known as Hawking radiation. It is not light escaping from inside the black hole. Nothing inside can ever get out. Instead, it is the fabric of space itself around the black hole, producing pairs of particles at the very edge. One falls in, the other escapes, carrying away a tiny fraction of the black hole's mass as energy. The effect is so small that for the black holes we know today, it is almost invisible. A black hole the mass of the Sun would take about 10 to the 67th years to evaporate completely, a number so large it makes proton decay look hasty. Larger black holes, like the supermassive ones at the centres of galaxies, last even longer. But even longer still means there is an end, if you wait enough years. And in the vast calendar of the universe, every page eventually turns. As the ages pass, there are fewer events to mark the passing of time. The last stars have burned out. Matter is rare and thin. The space around black holes is dark and cold, with no gas clouds or drifting stars to feed them. Without a supply of new mass, their only change is the slow, steady loss through Hawking radiation. Each escaping particle carries away a little more of their stored mass, their grip on the universe weakening molecule by molecule. Our proton may wander near one in this era, pulled slightly by its gravity, circling for a time before drifting away again. It might be swallowed, and if it is, that is not the end. Inside, the proton will meet the same fate as all matter that falls in. It will be broken down to its most fundamental components, its identity erased in the crushing depths. Yet even then, the story is not over. The mass it added to the black hole will one day be returned to the universe, transformed into faint radiation in the black hole's final moments. Those final moments are, in their own way, the brightest thing left in the universe. For almost all of a black hole's life, its Hawking radiation is too dim to see. But as the black hole shrinks, it grows hotter, its radiation more intense. In the very last second, after eons of almost imperceptible change, the black hole releases a final, blinding burst, all its remaining energy unleashed in one instant. It is a firework in a universe that has forgotten what fireworks are. This process repeats itself for every black hole, from the smallest stellar mass ones to the supermassive giants. One by one, across unimaginable spans of time, they vanish. Each disappearance is a reminder that even the deepest wells of gravity are not permanent. the great anchors of galaxies dissolve into a faint fog of photons, neutrinos, and other particles, spreading outward into the emptiness. When the last black hole fades, the universe changes again. It is not a sudden change. In fact, there is no one moment you could point to as the instant when black holes cease to exist. But the effect is absolute. Without them, there are no large structures left at all. No stars, no planets, no remnants to pull matter into new shapes. The only things that remain are the smallest building blocks, protons, electrons, neutrinos, and light, drifting apart forever. If our proton has avoided falling into a black hole, it will witness this transformation from a distance, passing through the quiet spaces where titans of gravity once held sway. If it has been swallowed, it will emerge again in the last light of the black hole's final breath, flung outward as radiation into a universe that has only darkness left to contrast with the faint glimmer. The end of black holes marks the close of the universe's grand architecture. Everything large is either burned out or evaporated. The scale of what remains is tiny, delicate, yet still enduring. Matter is no longer shaped into stars and worlds, but it has not yet disappeared entirely. The Protons chapter is not finished. The dark era has begun, and the last witnesses move silently within it. Even now, the universe is not entirely dead. The radiation from the final black holes, though spread thin, still travels outward, adding the faintest echo to the background. It will continue to do so for longer than any human word can measure, until even that light becomes too stretched by expansion to carry any warmth. And then, the only warmth left will be the memory of what once was. The last black hole fades, and the universe exhales into a silence so complete it feels like an ending. But this is not the end. Not yet. There is still matter here, still particles that drift through the vast emptiness. The stars, planets, and galaxies that once shaped the night have been gone for longer than the age of the early universe. The black holes that once ruled the darkness are now only memories written into the fabric of space. What remains is something smaller, quieter, and more patient than anything that came before. The universe has entered the dark era. It is not simply a description of absence, but a new condition of being. There is no starlight to see by, no warmth to touch, no great structures to give shape to the void. What exists now is scattered. Lone protons, stray electrons, and an endless sea of neutrinos that pass through everything without pause. Photons still travel, but they are cold, stretched to such long wavelengths by the expansion of space that they carry almost no energy at all. In this age, distance has lost much of its meaning. Expansion has pushed everything so far apart that interactions between particles are rare. A proton can drift for billions of years without coming close to another piece of matter. The paths of these particles are not guided by orbits or collisions, but by the slow currents of space itself, a tide so vast and unhurried that nothing in the early universe could have measured it. Our proton moves within this stillness. It does not remember the heat of stars or the weight of worlds, yet it has been all of those things. Once, it was bound to others in the tight embrace of an atomic nucleus. Once, it helped form water that trickled in streams and filled oceans. Once, it was part of the burning heart of a star where light was born. Now, it is alone, carrying no hint of its past except for the fact that it still exists. In the dark era, time feels different. Without cycles of stellar birth and death, without seasons or orbits, there are no natural markers. The difference between 1 trillion years and 10 trillion is as subtle as the difference between a single drop of rain and the ocean that holds it. Change, when it comes, happens at a pace so slow that it would seem motionless to any observer, though there are none left to observe. Occasionally a chance encounter will break the monotony. Two particles might pass close enough to interact, to scatter off each other in a brief exchange of momentum. But such events are vanishingly rare. The vast majority of the time, each particle drifts on its own path untouched. The universe is no longer a web of connections, but a scattering of solitary points. Energy still exists here, but it is spread so thin that it can no longer shape matter into the forms we once knew. The cold radiation from the last black hole still trickles outward, but it too is diluted beyond usefulness. What warmth there was in the cosmos has been stretched into nothing more than a faint hum in the background, quieter with every passing age. And yet, even in this deep stillness, there is persistence. Matter in its smallest forms continues to exist. The proton, our constant traveller, is still here, as it has been since the first moments after the Big Bang. It has survived every transformation the universe has thrown at it: collapse, explosion, fusion, and isolation. Now it survives in the simplest way possible, by doing nothing at all. The Dark Era does not have the drama of the earlier universe. There are no galaxies to collide, no novas to flare, no new stars to shine. But there is a kind of austere beauty in its simplicity, the vast, unbroken silence, the smooth, unchanging fabric of space. The fact that even here, so far from the warmth of creation, something remains. For the proton, there is no choice to be made. It will drift until the laws of physics decide otherwise. Perhaps it will endure indefinitely, outlasting every other particle in existence. Perhaps, as some theories predict, it will one day decay, transforming into lighter particles and releasing its stored energy into the emptiness. But that possibility is still unimaginably far away. For now it remains a solitary witness, watching, though there is nothing left to watch, as the universe coasts toward its final condition. The Dark Era is not a place of ending so much as it is a place without beginnings. Everything that was once dynamic has settled. The last of the great changes are over. What happens next will not be measured in the events, but in the gradual erosion of what is left. The proton may feel no difference from one moment to the next, but in the longest view, even it is part of a slow unraveling. There is a strange comfort in this. The universe has always been a restless place, always reshaping itself, always turning over what it has made. Now it has found a kind of stillness, a resting point in which the few remaining pieces can simply be. Our proton floats in this quiet like a seed in the wind, with nowhere to land but also with no need to. And so the Dark Era continues, not in silence that follows a catastrophe, but in silence that has simply always been here, waiting for its turn. The stars had their time, the black holes had theirs. Now it is the turn of the smallest things, the last players on the stage to hold their place in the dark. Time has stretched so far forward that numbers have lost their meaning. The early ages of stars and galaxies, which once seemed vast, are now as brief as a single heartbeat in a long and dreamless night. The Dark Era has lasted longer than all the bright chapters combined, and still it continues. The universe is not changing in ways that the human mind could easily notice. It has settled into a stillness so deep that even the concept of change begins to fade. One by one, the last protons vanish. Perhaps the decay is so rare that it takes longer than the lifespan of every black hole combined. Perhaps it is so subtle that no particle sees another vanish for ages upon ages. But over time, so much time that it cannot be compared to anything that came before, the number of surviving protons dwindles. Each one that goes is a small, silent ending. No flash, no sound, just a shift into a few lighter particles that drift away into the expanding dark. If our proton has made it this far, it is now more alone than it has ever been. It was born in a crowd, in a universe so dense and hot that it collided with its neighbours countless times every second. It has travelled through stars, planets, oceans, and the cold spaces between galaxies. It has been part of things larger than itself, much larger, and part of things impossibly small. Now there is nothing else left to join. It does not know it is the last. There is no awareness in it, no thought, no sense of victory or loss. But from the outside, we can imagine the weight of that position. Every atom that ever existed was built on the foundation of protons like this one. Every star was lit by the fusion of such particles. Every living thing, in every place it ever arose, was woven from them. To be the last proton is to be the final piece of the architecture that made the universe what it was. The space around it is not empty in the truest sense. There are photons, spread so thin and so cold that they are almost nothing at all. There are neutrinos passing without resistance, ghosts among ghosts. But there is no matter that could join with the proton to make something greater. The structures of atoms are gone. The possibility of chemistry, of planets, air, water, and life, has been erased. This is matter reduced to its simplest, barest form. It drifts, not toward anything, because there is nothing left to approach, not away from anything, because there is nothing left to leave behind. It is carried only by the slow expansion of space itself, a current with no destination. The concept of distance no longer matters, because there are no reference points, no markers to measure against. The universe is a smooth, infinite fabric, and the proton is one small knot in it, holding together for just a little while longer. If the theories of decay are right, its end will come without warning. One moment it will be there, exactly as it has been since it first formed in the cooling haze after the Big Bang. The next, it will have become something else, a few particles of light and a whisper of energy, scattered instantly into the immeasurable sea of space. There will be no observer to see this happen, no record kept, no echo loud enough to outlast the change. If the theories are wrong, if protons are truly eternal, then this last traveller will continue indefinitely. It will never change, never decay, simply existing as the universe stretches on without limit. That is not an ending either, just a different kind of forever, one in which there are no events left to witness, but also no force left to erase what remains. In either case, the proton's role as the final witness will be the same. It is the closing punctuation at the end of the universe's longest sentence. It does not choose to be there, yet it carries the sum of everything that has happened before. Every transformation the cosmos has ever known, from the violent ignition of the first stars to the quiet drift of the last black dwarfs, has led to this moment. And then, whenever it happens, after another unthinkable stretch of ages, there will be no more protons, no more matter, only the cold thrum of energy spread too thin to gather into anything new. The universe will be flat, featureless, and silent. Time itself may lose meaning, for without change there is no way to tell one moment from another. It will not be that time has stopped, but that there is nothing left for it to move. If the universe could feel, perhaps it would sigh here, not in grief, but in recognition, that every story, no matter how grand, contains within it the seeds of its ending. The last proton's passing will not erase what has been. Every star that ever burned, every life that ever took shape will have existed. The universe's memory is not kept in its present form, but in the fact that it happened at all. And so, for as long as it can, the last proton will drift. Not for purpose, not for meaning. Simply because there is still a space to drift through. The light it once knew is gone. The worlds it once visited are gone. The black holes that once guarded the deep are gone. Only the dark remains, and the quiet persistence of one small thing, holding its place at the very edge of time. It happens without ceremony. After all the epochs and transformations, after the stars and the black holes and the deep ages of drifting through the dark, the last proton's end comes quietly. There is no sound. There is no flash of light to announce the moment. No one watches. No one waits. It simply changes, slipping from one form to another, in the way a snowflake vanishes into water on the tongue. Instant, complete, and without resistance. In that change, something profound happens. Matter, in the form we have always known it, is gone. No more particles that can be bound into atoms, no more atoms that can gather into dust, no more dust that can form into worlds. What remains is energy, thinly spread across the infinite reaches of space, a haze so faint it cannot shape itself into anything new. The fabric of the universe still exists, but its threads have been pulled loose, left to float without purpose. The proton's decay is a transformation into lighter particles, photons, perhaps neutrinos, the same kind of building blocks that have travelled the universe since the earliest days. But unlike those first photons that burst from the newborn cosmos, these have nowhere to go that would change them. The space they move through is almost featureless. There are no stars to warm, no planets to strike, no structures to scatter from. They will simply travel, forever lengthening their wavelength as the expansion of space stretches them thinner and thinner. The end is not violent, it is not even sad, unless we choose to give it that meaning. It is, in its own way, the most natural thing the universe has ever done. Everything that has ever existed has changed form, passed through phases, and eventually yielded to something else. The last proton is no different. It just had a longer journey, measured not in billions of years, but in numbers so vast they overwhelm the language we have to describe them. If we could stand outside the universe and look at this moment as if it were a final page in a book, we might see it as the closing of a story. Every event that has ever happened in the cosmos, from the shaping of galaxies to the flicker of a firefly on a summer night, depended on the stability of matter. That stability has now reached its limit. The scaffolding that held reality together has dissolved, and all that remains is an echo of energy spread so thin it can no longer build anything new. Yet, to the universe itself, there is no sense of loss. There is no awareness of what has ended, no longing for what has passed. The particles that remain simply are, moving through a space that will never again be crowded. The decay of the last proton does not bring darkness. That was here already. Nor does it bring silence, because the universe has been silent for far longer than any star has shone. It is simply another shift in the balance of what exists. The haze of energy left behind is uniform, unbroken by the shapes of matter. It is smooth in a way the early universe never was. In those first moments after the Big Bang, matter and energy were mixed in turbulent swirls, uneven and restless. Now every irregularity has been erased. Every hill and valley in the landscape of the cosmos has been levelled. The result is a perfect sameness, a still surface that will never ripple again. For any being, if such a being could exist here, it would be impossible to tell if time was passing. There are no changes to measure it by, no cycles to mark one moment from the next. The photons move, but their movement alters nothing. The space they cross is indistinguishable from the space they leave behind. It is as if the universe has exhaled its last breath and settled into a state that will continue without end. The proton story is over, but the energy it releases continues its journey. In that way, nothing is truly lost. It is not the kind of continuation that builds new worlds or ignites new stars. It is a quiet continuation, the way a sound might fade until it is no longer heard, yet still exists as a vibration too small to notice. The last proton's energy will wander forever, a remnant of a remnant, without the ability to become anything else. If we think of the universe as a great tapestry, then the death of the last proton is the final thread being pulled free. The picture that once covered the fabric, with its bright bursts of starlight, its swirling galaxies, and the delicate structures of life, is gone. All that is left is the bare cloth, stretching in every direction, colourless and without pattern. And yet, even this is part of the same story that began in the hot, crowded seconds after the Big Bang. The forces that shaped the proton, that held it together through ages of unimaginable length, are the same forces that eventually allowed it to come apart. The laws of physics have not failed, they have simply played out their full range. In the long stillness that follows, the universe will remain, not in the way we once knew it, but in a form that asks for no more change. This is not an ending in the sense of disappearance, it is an ending in the sense of arrival, the point at which there is nowhere else to go. The slow ending of the last proton is one way the universe's story might conclude, but there is another possibility, one that is far less patient. Instead of drifting gently into stillness, everything could end in a single, silent moment. This idea is called vacuum decay, and it is not about the collapse of stars or the evaporation of black holes, but about the very foundation of reality itself. The universe is built on a set of physical laws, and those laws are written into the fabric of space in what physicists call the vacuum state. This is not the same as empty space. It is more like the ground beneath our feet, solid enough to walk on, reliable enough to build upon. But what if that ground is not the most stable it could be? What if, deep down, the vacuum of space is like a ball resting in a shallow dip on a hillside, stable for now, but not at the very bottom? If the laws of nature are in such a false vacuum state, then it is possible, at least in theory, for them to change. All it would take is one small region of space making the leap to a true vacuum, the most stable state possible. If that happened, the new vacuum would expand outward at the speed of light, rewriting the rules of physics everywhere it touched. And because it would move at light speed, there would be no warning, no time to notice, no time to prepare. From the outside, it would look like nothing at all. There would be no explosion, no burst of radiation, just the quiet replacement of one version of reality with another. But to everything inside the universe, it would be the absolute end. Every particle, every force, every structure would vanish instantly, replaced, or perhaps erased, by the new vacuum state. This is not an event we would see coming. Even if a bubble of true vacuum formed somewhere in the farthest reaches of space right now, it would reach us at the same moment we first became aware of it. The transition would be instantaneous, and it would not just change the arrangement of matter, it would change what matter is allowed to be. Atoms, stars, galaxies. None of them would survive the rewriting of the laws that made them possible. It sounds dramatic, but it is not meant to be frightening. In the scale of the universe, everything is temporary. The difference here is simply that the change would be abrupt rather than gradual. Instead of the last proton drifting alone for unimaginable ages, the whole of matter, energy, and space would end in the same breath. The story would close not with the slow dimming of the lights, but with their sudden absence. From the perspective of the universe, there is no preference. The laws of physics have no attachment to time's pace, whether the end comes in 1 trillion years or in an instant. It is simply the next chapter in the story written into the structure of reality. The difference is one of texture, not of meaning. If this happened, there would be no remnant to drift, no haze of photons stretching into the void. Whatever lies beyond, if anything lies beyond, would not be the same universe in any form we could recognize. It might be empty. It might be filled with new particles, new forces, and new possibilities. It might be another beginning entirely, though one we would not be part of. Some physicists think the risk is small, perhaps so small that it will never happen at all. Others think it is inevitable, given enough time. But in a universe where we already deal with timescales of 10 to the 34 years for proton decay, and 10 to the 67 years for black hole evaporation, enough time is difficult to measure. What matters is that it is possible, and that possibility is part of the fabric of the cosmos, just as much as the possibility of stars forming or galaxies colliding. And there is a strange kind of mercy in it. In a slow ending, the universe lingers in darkness, with particles drifting endlessly, unable to create anything new. In vacuum decay, there is no drawn-out stillness. There is no waiting for the last light to fade. The end is sudden, complete, and final. A clean break between what was and what will never be again. In the absence of an observer, it would not even be experienced as an ending. It would simply be the last moment, and then nothing that could remember there had been a moment at all. The universe would not mourn itself. It would not even notice the transition. The change would be as natural to it as the cooling of the early plasma, the formation of the first atoms, the collapse of the first stars. If we think of the slow ending as the universe falling asleep, then vacuum decay is the universe blowing out a candle. Both lead to the same darkness. Both are part of the same truth, that nothing, no matter how vast or ancient, remains unchanged forever. And so, whether the final chapter is a long drift into stillness, or a single, silent leap into something entirely different, it is still part of the same story we have been following since the first second after the Big Bang. It is not the pace of the ending that matters, but the fact that every ending in its own way completes the arc that began in the beginning. When the last changes are over, whether they arrive as the slow unwinding of proton decay or in the instant of vacuum collapse, the universe reaches a state unlike any before it. There is no matter left to shape, no forces at work strong enough to build new structures, no unevenness for gravity to gather. All that remains is energy spread so evenly, so perfectly, that nothing anywhere is different from anything else. Physicists call this the heat death of the universe. It is not heat, as we know it, not the warmth of sunlight or the comfort of a fire. It is the opposite, a condition in which all energy is evenly distributed, so there is no gradient, no higher and lower, no warmer and cooler. Without a difference, there is no way to do work, no way to cause motion, no way to light a star or grow a plant or even tick the smallest clock. The universe has reached maximum entropy, the point at which it cannot become more uniform. In this condition, even the concept of time becomes slippery. Time is, at its core, the measure of change. We know a moment has passed because something is different than it was before, but here, in the smooth sameness of perfect stillness, there is nothing to compare, nothing to measure. A second, 1,000,000 years, 1,000,000,000,000 years, all would feel the same, because nothing would happen to tell them apart. This is not a sudden stillness, but one that settles so completely it becomes the natural state. In the early universe, stillness was impossible. Every point in space was changing, colliding, expanding, cooling. Even in the long ages of stars and black holes, there were cycles, patterns, events. Now there are no events. The universe is not merely empty. It is without contrast, without edges. And yet, it is not gone. Space still exists. The faint hum of background energy is still there, stretched to wavelengths so long they cannot be gathered, cannot be felt. The structure of space-time may remain, though it holds nothing. It is a stage with no actors, a sea with no waves. If there were an observer here, though there is no way for such a thing to exist, they would not see darkness in the way we imagine it. Darkness, for us, is the absence of light against a memory of light. Here there is no comparison. It is not black, not white, not grey. It is simply uniform. It is the absence of difference. This state could last forever, or it could be the quiet before something else. Some theories suggest that even in maximum entropy, rare quantum fluctuations could spark tiny regions of change. Brief, local departures from stillness that collapse again as quickly as they appear. These would be like ripples forming and vanishing in the calmest sea, too small to affect the whole. Others imagine that the entire state could be broken by something as dramatic as a new Big Bang, a fresh inflation of space-time that would replace the endless calm with a new burst of creation. But if nothing like that happens, then this is the final horizon of the universe, the heat death. Beyond it lies not destruction, but the endless continuation of sameness. It is an eternity without events, a clock without hands, a book with no new words to turn to. In such a place, the universe cannot be said to be old or young. It is simply there. It is tempting to think of this as a kind of death, and in a way it is. The creative phases are over. The energy that once lit a trillion suns is now spread too thin to light even one. But it is also a state of peace, the final settling of every motion, the balancing of every imbalance. The struggles of gravity and expansion are done. The arguments between light and darkness, hot and cold, matter and void, have been resolved into a perfect agreement. For all the vastness of its history, the universe has been moving toward this from the beginning. The first unevenness in the cosmic microwave background, the first clumping of gas into stars, the first collapse of those stars into heavier elements, each was part of a chain of changes that could only end in stillness. Not because the universe sought it, but because the laws of physics guided every step along the way. And now, here it is. Whether reached by slow fading or sudden transformation, the heat-death horizon marks a point beyond which there is no further journey to take. It is not a boundary in space. There is no edge to cross, but a boundary in possibility. Nothing more can happen, because everything that could happen already has. If the story of the universe began with a great explosion, it ends not with another, but with this. The quiet breathing of a cosmos that no longer moves, no longer changes, no longer needs to. The silence is complete, but not empty of meaning. Every event that ever occurred still exists in the chain of cause and effect that led to this moment. They're gone in form, but they remain in the way the universe is shaped, even if that shape is now smooth beyond recognition. And so the heat-death horizon is not just an end. It is the final shape of all beginnings, the place where every light and shadow, every motion and stillness, every rise and fall has resolved into a single endless balance. Beyond it, time itself drifts into irrelevance. The story is not being told anymore, but it has already been told, and the telling has reached its last word. The universe, in its final stillness, seems like it could last forever. Yet even forever, in physics, is only a kind of pause between changes. Some theories whisper that the end is not truly an end, but a turning point. That from the quiet after heat death, or from the collapse of everything into a true vacuum, something new could begin. The idea is not certain. It is not even something we can test with the tools we have. But it has a quiet appeal, that endings may carry within them the seeds of beginnings. One possibility is that of a cyclic universe. In this view, the cosmos is not a single story with a single arc, but a series of stories, each one rising and falling, each one giving way to the next. The Big Bang would not be the ultimate beginning, but simply the most recent beginning, one in a long chain of expansions and contractions. In such a cycle, the heat death we imagine now would eventually give way to something else. Perhaps a collapse back into a hot, dense state, or perhaps a sudden reset into an entirely new phase of expansion. Another vision is eternal inflation, in which the universe is part of a larger multiverse. In this scenario, the space we know is just one bubble in a vast foam of bubbles, each a universe with its own laws and constants. Even if our bubble grows cold and still, others may continue to form elsewhere. In some distant place, a patch of space could begin inflating again, giving birth to a new cosmos, perhaps with new particles, new forces, new chemistry. We would not be part of it, but its existence would mean that creation itself is never fully gone. There is also the thought of quantum fluctuations, random, temporary disturbances that arise from the uncertainty built into the fabric of reality. Even in the smoothest sea, tiny ripples can appear. In the extreme emptiness of a heat-dead universe, A rare, massive fluctuation could briefly bring together enough energy and matter to create something stable. Most fluctuations would collapse almost instantly, but perhaps by chance one could spark into a self-sustaining expansion, a new universe born from what seemed like nothing. In all these ideas, the proton we have followed would not survive into the new chapter. It has already given up its form, returning its energy to the smooth background. But in another sense, it might not be truly gone. The energy that once shaped it could be drawn into the first events of a new cosmos, transformed into new particles, which could form new atoms, new stars, new worlds. Its history would not be erased, only rewritten in a different script. It is tempting to imagine that somewhere, far beyond what we can see or measure, such a renewal has already begun, that even while we picture our universe settling into stillness, another universe is just lighting its first stars. Perhaps there are countless others, each in its own place along the arc from beginning to end, and perhaps in one of them, a particle much like our proton is starting its own journey, through heat, through light, through life and darkness, without ever knowing that it is part of a much larger rhythm. But it's just as possible that none of these things will happen. The heat death could be final, the smooth stillness unbroken. And if that is the case, then this single universe will remain as it is forever, with no rebirth, no new story. That possibility is no less meaningful. It would mean that every event, every light, every fleeting moment of beauty happened exactly once, never to be repeated. It would make the history of the universe not less precious, but more so. The whisper of rebirth is not a promise. It is an invitation to wonder, to think that the laws of physics might hold more possibilities than we have yet seen, that the stillness we imagine could be the pause before another song begins. And even if we cannot hear that song, it may still be worth knowing it could exist. For our proton, there is no difference. It has lived its span, through fire and ocean and darkness, through the rise and fall of stars, through the opening and closing of cosmic ages. Whether the story continues somewhere else or stops here, its part in it is complete. The possibility of rebirth does not change what it has been. It only places that journey in a larger frame, where even the end of one universe may be only a chapter in a story that has no true beginning or end. And perhaps that is the quiet lesson here, that the universe, like the proton, may be both temporary and eternal at the same time. Temporary in its form, eternal in the way it passes its energy forward, even if forward leads to something we cannot imagine. That in the silence after the last light fades, there may still be the potential for something new to stir. In that sense, the heat-death horizon is not a wall. It is a horizon in the truest sense, the edge of what we can see, beyond which we cannot know. And like all horizons, it invites us to wonder what lies past it, even if we never cross it ourselves. And so we return to the beginning. Not to the hot, blinding light of the first second, but to the place where the story now rests. The proton we have followed has lived a life longer than the galaxies, longer than the stars, longer than anything we could have imagined when it first took shape. It has seen every age the universe had to offer, not by choice, not with awareness, but by simply being, present through the unfolding of all time. It was there when the universe was so dense and hot that nothing could stand apart from anything else. It was there when the first light spilled into the darkness, when gravity pulled scattered gas into blazing stars, when those stars burst and scattered their riches across the void. It has been a part of planets and oceans, mountains and clouds. Perhaps it once sat in a drop of water that clung to a leaf under the light of a newborn sun. Perhaps it rested in the curve of a bone, or in the lattice of a crystal deep underground. Wherever it was always moving, always carried forward by the great slow current of the cosmos. It has survived the swelling and fading of stars, the long ages of drifting through interstellar night, the quiet of galaxies slipping beyond sight. It has waited through times so vast that human words begin to lose their meaning. And even when the universe emptied itself of light, when only the slow embers of ancient stars remained, it endured. It endured when the last black holes sighed their final breath of energy into the void. It endured until the moment when matter itself could endure no more. Now the proton is gone, not lost, but changed, folded back into the soft haze of energy that will wander forever through the stillness. The shape it once held no longer exists, but the essence of what it was is not erased. It is part of everything that came before, and part of whatever, if anything, comes after. And in this, there is a strange reflection of you. The atoms in your body are not as old as this proton, but they are still ancient. They were forged in stars long before the sun was born. The iron in your blood, the calcium in your bones, the carbon in your skin, all of them were once scattered dust drifting between the stars, waiting for the chance to be part of something new. You are, in a very real way, a brief gathering of ancient matter, brought together for a moment in time before it moves on to other forms. The proton's journey and your own could not be more different in length or in awareness, but they are both made from the same substance, shaped by the same laws, carried along by the same unfolding story. To know that is to feel a kind of kinship with the universe itself. You are not separate from it. You are a chapter in its history, just as it is the setting for yours. And now, as the story of the proton comes to rest, so can you. The universe will keep its quiet watch, whether through the long drift of heat death or through the sudden leap into something new. Whatever happens, the atoms that make you are part of that great continuity. They have travelled far to arrive here, in this moment, and they will continue to travel long after you have moved on. There is comfort in that, in knowing that you are part of something so enduring that even the idea of an ending cannot contain it. So let the vastness be what it is. You do not need to hold it all in your mind. The stars, the galaxies, the unimaginable distances, they have their own pace, and they will go on without your effort. You can set them down now, like a heavy book whose final page you have turned. You can let yourself drift, as the proton once drifted, carried by currents you do not need to see to trust. Close your eyes and let the shapes of the universe fade into a soft blur. Let the first light and the last shadow meet in your thoughts until they are the same gentle grey. Let the great span of time shrink to the single moment you're in now, where your breath rises and falls like the smallest tide. The proton's journey is complete, your day is complete, and in the quiet that follows, you can rest. The universe is wide enough to hold everything that has ever happened. It is quiet enough now to hold your sleep. It has waited through billions of years, and it can wait through the night. Sleep well, little witness of all time. You are made of the same ancient matter as the stars, the same enduring substance as the proton, the same fabric as the universe itself, and as you close your eyes you are part of it still, and it is part of you.